name is Joel DeLeon, and the NAE challenge that our group and I chose is to make solar energy more economical. A quick rundown of this challenge is pretty simple. Currently, there's two main challenges facing solar panels in the United States. The first challenge, I guess you would call the first problem, is that solar panels are currently operating at 20 to 30% efficiency, which is pretty bad. And the other challenge is that they have no form to store the energy. So if you don't use the energy right away, they can only hold it for so long, and that's kind of a problem because we need solar panels to work at night when it's cloudy and when it's raining. It's pretty easy, pretty self-explanatory. First, we have a start, and then the next step is we extract the data of the classes and the energy that was given to us by the professor. The classes range anywhere from 1 to 10, and the energy ranges from megawatts to kilowatts to terawatts per hour. Next, we have to assign the limit of solar insolation to a capacity factor, which then is also corresponding to a class. It sounds confusing. It's not that hard. Each class has a capacity factor, and that capacity factor also has a solar insolation. They're all equivalent. Solar insolation, for anybody that doesn't know or understand, is just the peak sun hours, which could also be stated as the hours at which the sun is at its maximum, at its brightest, that is not cloudy, that is not raining, such. And you equate all of those three. Next, you calculate the mean for the solar insolation for each class. Say class 1 has solar insolation from 3 to 3.5. We really don't need that. We just need the average so we can work with the means. So you just calculate the means for each solar insolation and you'll be good. Next, you have to convert the energy from megawatt hour per year to kilowatt hour per year so it can be consistent with the rest of our data from the data we're going to input later. It's not that hard. Next, we have to create a matrix with the same length as a placeholder. What that means is that we have to create a matrix of two columns. The first column will be the classes that was given to us from the data from our professor, and the second column will be the energies that range depending on the classes. The reason we do this is so that we don't have to extract the full data later on. We could just have this matrix as a placeholder in case we need any specific value later on in our code, which we will. And that will save us extra lines, extra space, and extra time. Step 7 is we run a loop through the code to see if any of the classes from the data that was given to us matches the classes from the capacity factor and the solar insolation that we talked about earlier. If any of the classes from the data given to us does not match any of the classes that we have from the capacity factor and the solar insolation, then unfortunately that's beyond our data. That is a limitation that we have. Our data doesn't account for that because of the lack of data that we have, and we just have to terminate the code. However, that is not the case, and the classes do match, so we just go on through to step 8. The next step is pretty simple. All we have to do is just store the value of the solar insolation associated to the location. So the solar insolation were the values that we got in the beginning, whenever we equated it to the capacity factor into the class. All we're doing now is just adding this column of solar insolation to the matrix that we had before. The matrix from step 6, where it was the class, column 1, the energy, column 2. Now we're creating a new column, column 3, and we're going to put the solar energy in that column. The reason why we're doing this is because now that we have all those 3 in one column, it's easier to find the area. So the area is equal to the energy divided by the insolation. Here is my proof. It's pretty simple. It's not that hard. And then now, since the area is massive, since we're talking on a large scale, we just convert it to kilometers to keep the number smaller, easier to work with. And then we take that max to find the maximum area used inside the United States. Once we find the maximum area, on the matrix given to us. It's pretty simple. Now we can find its location, where it's at on the matrix, and then once we know its location on the matrix, we would just look over and we can see the associated class with that location, and then from that, it tells us which class is most commonly used in the United States. It tells us what area is most commonly used in the United States. From that, we can also find what capacity factor is most commonly used in the United States, and we can go as far as to even say what is a common solar installation for the United States based on the data given to us. Okay, this is part B for our algorithm. In this part, we're gonna see how many years it takes for a solar panel to pay itself off and then to start generating revenue and profit for the owner, targeted towards families, households trying to do this. So for this section, we're going to need two input statements from the user. Why not is the installation year, is the year that you want to purchase the solar panel and put it in. And H is the solar installation for the region. How many peaks on hours you get in your area, which is important because it ties into the capacity factor. Using these two, we derive an equation where it will take Y number of years to pay off the solar panel, for the solar panel to pay itself off. The equation is pretty simple. It's just the price for the solar panel times 1,000 divided by the price for the fossil fuel times H times 365. If you're confused from where the price for the solar panel and the price for the fossil fuel comes from, it's pretty simple. Given the data that we found on price trends for the solar panel, you just plot the graph from the data points, and then once you have the graph and the data points plotted, you find a polyfit curve. In our case, we used an exponential one because it tends to fit the curve better than power linear. And it came out to B for the solar times E raised to year times M for the solar. And for fossil fuels, we used the power function because it fit the graph better. It's just B for the fossil fuel times the year raised to M of the fossil fuel. It's not that hard. It's just polyfitting the curves. Once you get those two years, those two price equations, you just plug them in and you put any hypothetical year in the future, 2016, 2020. Once you get that, you find the year, why not 15 years, 16 years, and you just add it to the year that you bought the solar panel, why not? And then that'll be your new year. If you run our code, a menu window will come up. Option A is targeted towards investors and companies and engineers of that sort. If they choose to run our code, then our code will execute a series of different steps and functions, and then the end result will be a formatted output that will state the most common class that is used within the United States, the most common solar installation depending on the area, and the most common capacity factor. This is helpful towards engineers because it tells them where we're at right now, currently in the United States. And we've also built in a function that will tell engineers or whoever the user of this code whether these solar panels are functioning economically or efficiently. Choose part B for our code in the menu, then that'll redirect you to a section in our code that's dedicated for family, households, and individuals who want to purchase solar panels. If you do, our code will run a series of different functions and programs that will generate three different graphs. The first graph is the actual experimental data that we have for fossil fuels that shows it is clearly increasing over time. The second graph is a polyfitted curve that fits the first experimental data for the fossil fuels that is increasing over time. And the third graph is a pricing trend for solar panels that clearly shows that it is decreasing over time. So what our data is telling us is that fossil fuels are getting more expensive and that solar panels are getting cheaper and cheaper to manufacture. Aside from that, the code will ask for two inputs. Y naught is the installation year, and H is the peak sun hours in the region that they're wanting to buy it in. If the user can accurately put these two inputs, then our code will generate a number, variable Y, that will indicate the total number of years that it will take for the solar panel to pay itself off and then start generating revenue for the individual, which will be 100% profit. Unfortunately, though, there are some limitations to our code. Some of the limitations include extrapolation. Since the data is only for this decade that just passed, we can't really say that it'll be steady or that nothing will happen over the next 50, 70 years and that the data will still be exactly accurate. Another thing is that we assume the price for fossil fuels won't fluctuate when we put it into the equation to predict the number of years. Of course, we know that's not true. It will fluctuate, but then it wouldn't work with our equation. We assume that the United States does not hit a depression, economical depression, and that prices don't go up or down, and that the economy is relatively stable during these years. We also assume that the family or individual knows what the peak sun hours are, but many people don't know that, and if they do, it's really hard to calculate when sometimes it might be sunny, sometimes it might be rainy, cloudy, thunderstorming, etc. And we also include that the solar panel that is given by our experimental data already comes with the capacity factor included. Now, we spoke about the capacity factor earlier, and what that means is basically right now the solar panels cost $3.5 per watt to install. However, our graph shows that they should cost roughly $0.7 per watt to install. However, the big difference of this is that this cost is because we know that the capacity factor is working at 20%, which is the United States average. This capacity factor, however, would be working at 100%. So you see that there's a 5 times difference, and if engineers could relatively fix that or shorten the gap, then they would save everybody money. It would save corporations money. If we could get capacity factors to 100%, it would save us 5 times as much money per watt that we're spending. So that is the incentive.